So in this set of videos and slideshows, we're going to try to relate the difference between the shape and the wall. What common question, or what I want to mean with this is, what if we wouldn't have all those fittings? Let's say, for example, we wouldn't have this elbow and we have not this here, this elbow right here, we have no expansions here or compressions. If we wouldn't have all those fittings and valves, how long will our pipe be given a system? Of course, this has a system. Let's say it has a pump. It has a certain amount of energy which goes in the pipe, and it needs, or it loses energy in each one of these fittings. So imagine if we wouldn't have that fitting, how long will the pipe go? Of course, you will expect it to go larger because you have less friction. So for example, for this actual system, we could say 100 meters. And imagine we had all these straight, we have no fittings. We could have even maybe 150 meters, I don't know, it's an example. So what we want to do is essentially, we have the pipe wall friction, and we have the fitting or valve or accessory friction. We want to relate those energy losses, and in both cases, as velocity increases, the energy loss is greater, and actually we have this velocity head. So that's what we have in common. So whenever you want to relate anything, you need to have the mathematical expression. So I have this one for wall, and this one goes for fitting. So first things first, this velocity head is similar. So actually, the only difference is this and this. So let me get this and this. Actually, we could define this right here. Let me define it right here. This is the length equivalent. So we could say that given k equals, I don't know, maybe 0.1, if we want to force the length and the diameter of that pipe, it's easy. We just need to do this 0.1. We say that k equals FL in diameter. So if we have k and we want to force the length and diameter of the pipe, we just need to find this. Okay. So you may think of this as the length this accessory will have if it is transformed or converted into a pipe. So for example, you have this elbow. Maybe if we wouldn't have this friction loss, we could have this length of pipe. And this is good because we can relate length and diameter. Let's see it here. For example, we have this right here, we have this value here. And if it's smooth, we will have this value here. If we use a moderate rough pipe, what will be the equivalent length? So let's see. So because this is very rough, we will probably have a very long equivalent of pipe. And because this one is very smooth, we don't have that, let's say, that high energy. So we have right here, it will be a very small length. So what I want you to tell you guys is that even though it's the same fitting, this is a little bit more rough and this is very smooth. So when you want to turn this into a pipe equivalent, you will have a very long pipe because it's very frictious, and this will be a very small pipe. Okay. Now let's do it with some numbers. Okay, we got the K here. So as I told you before, we can have this right here. This is the FT equivalent and the L divided by diameter equivalent. So you could use this right here. Instead of using K, we have this. And this is very good because we will be then adding different friction factors. L in D is a constant because the length of the diameter won't change. So we can do this. You have this right here and this right here, and you will end up with this value, and you will get HF, which is right here. Okay. This is just theory, guys. You don't need to apply it. If you think or you feel more comfortable with the K value, you could use it. Actually, the formula will be pretty similar. Take out the velocities and you're done. Whatever approach you use, you should get the same value of friction loss. So in conclusion, you could add all the frictions in one single term, then multiply it by the velocity of that pipe, and you're done. You get your friction right here in one single term, which is the idea. You want to get this as a number. This was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, if you were analyzing or studying pumps, you have it here, the pump block, then you have the sections. If you were, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. If you were studying positive displacement pumps in rotatory and reciprocal are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.